Hello and good day, Mike Adcock here with the fourth installment of Tropical Cyclone Reconnaissance tutorial videos. In this particular video I will discuss high density observations. This has really changed how meteorologists and storm enthusiasts alike use Hurricane Hunter data. About 10 years ago, if you wanted to follow along during a Hurricane Hunter mission, really all you had was the RECO observations as well as the vortex data messages, but generally people got any sort of recon data from the National Hurricane Center forecast discussion. Nowadays it's a lot different. We get these observations almost in near real time. We get a kind of an insight on what the National Hurricane Center may put in their upcoming bulletin, because you're getting this data almost live. It's like you are virtually storm chasing the tropical cyclone. Well, from the National Hurricane Operations Plan, high density observations are required every 30 seconds en route and for invest areas and during fixed patterns. Now what this means is generally you will start seeing high density observations coming out as an aircraft is taxiing or preparing to taxi to the runway at be it MacDill or Keesler Air Force Base or wherever they're forward deployed. High density observations are automatically numbered, and they are a separate numbering scheme from the other observations. You'll see, like a RECO ob number 1 comes out, then vortex data message number 2, then a dropson number 3. Those are sequential in their own right. High density observations are separately numbered. And generally in each bulletin you'll get about 20 lines of code. Now, since they are representing 30 seconds of data, you're basically getting 10 minutes worth of information. So these bulletins are transmitted every 10 minutes, and you can get them off WMO header URNT15 for the North Atlantic or URPN15 for the Pacific. KNHC is the general identifier that is used. NOAA aircraft will use KWBC for secondary means and KBIX for Air Force Reserve. And this is definitely used when there are multiple aircraft flying the same storm. You get a storm system that's approaching. If Air Force and NOAA are flying the same bird or same plane, you'll see multiple identifiers used. And you can get all this information live from the National Hurricane Center's webpage over on the Recon section. We'll actually look at that a little bit later on. Alright, so I'm going to take a simple one-line clip from Hurricane Katrina. Very top line, of course, is our WMO header, so URNT15 identifies this as a high-density observation. KNHC, of course, is the main National Hurricane Center identifier and the date time group. So this was from the 28th day of the month at 1426 Zulu. Next line is our mission identification line. Of course, as standard, aircraft tail number, mission number, cyclone number, basin identification, storm name, and then this is what I was talking about earlier. This is our observation number. These are separate. You'll get, the first 10 minutes of data are ob number 1. Second 10 minutes of data is ob number 2, and so forth. And then that very first ob sets the date time group. Regardless if the day changes, it will stay this. This is the date and time, or the day rather, the first observation was taken. Alright, let's get into the meat and potatoes of this thing. First column, and I say column because usually there's 19 more lines after this, but this first column is our date of the time of the observation. Hours, minutes, and seconds. Now, this is a 30-second window here. The aircraft is constantly spitting out information. Consider the aircraft a automated weather observing system. What they do is, for 30 seconds, they average the information that it's sensing. And the midpoint is identified here. So in this particular case, everything on this row represents the average from 1422 and 15 seconds through 1422 and 45 seconds. At the next line, the 1423.00 line, would be from 1422 in 45 seconds through 1423 in 15 seconds. Alright, so this is at 14 hours 22 minutes 30 seconds, and then our next two columns is our latitude and longitude. Now, I want to emphasize this is in degrees and minutes. So this first column, 26 degrees 12 minutes north, 87 degrees 52 minutes west. Now, one of my pet peeves, not just in general, is people mixing up degrees, minutes, and decimal degrees. Why that becomes important is if you're actually applying it into a forecast or emergency management information. There is a huge difference at times between degrees, minutes, and decimal degrees. For instance, 27.52 is completely different from 87 degrees 52 minutes. This is almost 88 degrees. So one good way to convert from degrees, minutes to decimal degrees, and I say that because decimal degrees is what's used by the National Hurricane Center in their advisories. You take the minutes and simply divide by 60. So in this case, 26 degrees 12 minutes, take that 12, divide by 60, and you get 0.2. So 26.2 north, and then 52 minutes, you divide that by 60. That will give you 0.8666, so 87.87 degrees west. Alright, enough about that. Moving on to the next column is our static air pressure. This is the pressure where the aircraft is at. Now, typically the aircraft try to fly at a standard atmosphere. This particular case, this is reported in tenths of a hectopascal. The decimals and thousandths, if required, are omitted. So in this case, the aircraft is flying at 701 hectopascal. Generally, you will see aircraft flying at 700, 850, 925, and 1000 hectopascal. Now, why this is important is this kind of goes hand in hand with our next column, geopotential height. This is the geopotential height of the aircraft in meters. In this particular case, 3,057 meters. This is important because as you're flying through a storm, obviously as you get in toward the eye of the storm, your pressure decreases. Well, the aircraft is set to fly at a given height, so in this particular case, it's going to fly at 700 hectopascal. But doesn't mean you're going to be at steady flight. Because the air pressure is decreasing, while this row will be generally constant, you will see your height decrease as you approach the center. What that means is, okay, in the periphery of the storm, our pressure may be 1000 hectopascal, but we get into the center of the storm, it's really like 925 hectopascal. So that means the height in which 700 millibars is found, or 700 hectopascal, would be found much lower. So we'll get into more of that when we get into our example. Next column is generally used for surface pressure. This is a little tricky here, but generally when the aircraft is in the fix, this is going to be your extrapolated surface pressure. How do you know? Well, first off, you go over here and you see if the aircraft is below 550 hectopascal. So we're looking at this column. Now when I say below, I'm saying altitude-wise. So as we know, if an aircraft goes up into the atmosphere, the higher it goes, the less atmosphere is weighing down on it, so the less pressure is present. So when I say below 550 hectopascal, I mean lower in the atmosphere, or this number being bigger. So since 701 hectopascal is lower or below 550 in the atmosphere, then this is surface pressure. So in this particular case, again, tenths of a hectopascal, decimal and thousands omitted, so our extrapolated surface pressure is 928.2 hectopascal. Now when we're in transit, flying up above 550 hectopascal, again that means this column, the number is less than 550, then this is simply a D value, which is our deviation from standard atmosphere. It would be reported in meters, 5,000 is added for any negative values, and we'll look at that a little bit later on as well. Next column, simple enough, air temperature in tenths of a degree Celsius, so this case is plus 10.2 degrees Celsius. Next column, same thing, but for dew point, again, 10.2 degrees Celsius. Now this is the column that gets a lot of people's attention. This is our wind direction and speed. This is a 30-second average. First 3 digits is your wind direction. So in this case, the wind direction is 141 degrees, which would be southeasterly. The next 3 digits is our 30-second average wind speed in knots. So in this particular case, 153 knots, or 176 miles per hour if you do the conversion. The next column is a 10-second gust. Again, over that 30 seconds of time, what was our 10-second gust? And in this case, 166 knots, or about 191 miles per hour. Now, this, I want to emphasize, is not your surface wind speed. This is not your surface wind direction. This is at flight level, again, at 3,057 meters above the water. Now, there is a paper that James Franklin wrote back in 2003 that talked about correlations between flight level winds and surface winds. And what they generally saw was at 700 hectopascal, which this observation represents, this wind speed, both columns here, is usually reduced to about 90% in the eye wall, or 85% in the outer vortex during convection. And the numbers change. If you're flying at 850 hectopascals, or about 1,500 meters, the number is at 80%. If you're down to about 925 hectopascal, or about 750 meters, the number you're looking for is 75%. And then if you're flying in invest at about 300 meters, you're again looking at about 80%. So why is this important? Let's use this 153 knots, bringing up our calculator here. 153 knots, this is at 700 hectopascal, and I know by the wind speed that this is in the eye wall. So we're going to take 153 and simply multiply it by 90%, which gets me about 137.7 knots. At this point, I can take this and go, okay, 137.7, that rounds up to 140. We're looking at sustained winds of about 140 knots, which would be a Category 5, which we knew Katrina was. You don't often see, but on occasion, you'll see the gust use 166. Again, same application, 90% would be about 150 knots. So you've got options there. Interestingly enough, you take this 149 knots and you look at the next column. This is our stepped frequency microwave radiometer. Generally not the best tool, but okay. I just got an observation of 100 and you know, if I reduce the 166 down, about 150 knots. This stepped frequency microwave radiometer confirms that at 148. Again, 10-second average wind speed. So we're looking at possibly a 150 knot storm just looking at this line of data. Alright, next column is rain rate. Again, this is derived from the stepped frequency microwave radiometer, and this is in millimeters per hour. The 999's there, kind of a not getting any reading, so but usually this would give you the rain rate per hour. And then this is a very important column that kind of gets overlooked during crazy moments. This is the quality control section. What you're looking for here is double zeros. If you see 2 zeros here, this line can generally be used verbatim. All parameters are within the normal range of accuracy. You see here, column 1, if this first digit is a 1, our latitude or longitude is off. If it's a 2, our geopotential altitude or static pressure is off. And then a 3, both numbers are off. You rarely see this off of 0. The second digit, though, is your looking at temperature, dew point, flight level winds, and the stepped frequency microwave radiometer, represented by 1, 2, and 3. 4, 5, and 6 is a combination of those, and then 9 is pretty much everything's messed up. Alright, let's use an example here. This is a data set from Hurricane Felix back in 2007. Now, if you notice from this top line, URNT 15, this is a North Atlantic HD observation set. This is using the WBC identifier because this is NOAA mission 3 or NOAA 3 flying. Hurricane Felix, this is OBSET 28. Alright, now in this particular case, when you get this block of data, rather than looking line by line, it's actually better to look horizontal down the column, okay? Again, this is your time, so 10 minutes worth of data from 12:24 through 12:33 and 30 seconds. Again, these next two lines are your latitude and longitude, so you're seeing basically 13 degrees 55 minutes through 14 degrees 23 minutes, and then for longitude 77 degrees 11 minutes through 76 degrees 50 minutes. Alright, your next column here is our pressure. Again, remember, for major hurricanes, we're trying to fly generally about the 700 hectopascal flight level, and you see that definitely with this column. I mean, it's not going to be perfect. I mean, turbulence and all sorts of other parameters, you're going to be in the neighborhood. So just shy of 700 hectopascal, not too bad. So flying at 700 hectopascal. Now use this in conjunction with this next line. So the airplane thinks it's flying relatively in steady flight, about 900 or about 700 hectopascal. But this is our geopotential height. So we start off at 3,111 meters. Now you notice the aircraft is descending, and this is as we're going through the eye. Again, the lower pressure in the eye, the aircraft is going to naturally go downward because it thinks it's still flying at the steady state. Well, we get down to 2,629 meters. That's a significant drop. We dropped 482 meters. That's about, if you're not friendly with the metric system, that's about 1,581 feet. That's a pretty big drop. If you look back, if you remember back to Hurricane Wilma, they initially flew into it at, there was one particular pass that they flew in at 850 hectopascal. Well, the system was rapidly intensifying, and they, because the aircraft naturally descends as it goes into the eye, they were getting uncomfortably close to this surface. Obviously, hurricane hunters want to fly as low as they can to get the most accurate data, but at the same time, you don't want to fly too low for obvious reasons. So in that particular case, they had to abort, and in the eye, they ended up climbing up to 700 hectopascal. So when you see this significant drop, in this particular case, almost 500 meters of change, that identifies the strength of this storm. And of course, Hurricane Felix was a monster of a storm. Alright, next column is our sea surface pressure, extrapolated, of course, because we're flying at 700 hectopascal. So we start off at about 995.8 hectopascal. We drop, and we get into the eye at about 936.5 hectopascal. So very strong storm. I want to emphasize, though, this is extrapolated. It's a good start, but there's a couple of things you want to look at. You also want to look at what's your wind doing. And it's extrapolated. The best source of data is going to be a drop sonde. They generally correlate, but you will see hurricane hunters and the National Hurricane Center use the drop sonde reading over this extrapolated reading. They'll use the extrapolated as a backup. Alright, next column is our temperature. And I'm going to look at both columns, temperature and dew point, at the same time to get an idea of the moisture. We're flying through the eye wall here, these first few lines. Notice it's nearly saturated. The colder the temperature, the more severe of the showers that we're running through. So we get down to about 10 degrees Celsius, nearly saturated, a dew point depression of 0.3 degrees Celsius. So it's almost completely saturated. We get into the eye though, notice how quickly within a couple minutes our temperature climbs almost 13 degrees Celsius up to 22.9 degrees. Notice our dew point also drops off to about 4.5 degrees Celsius. Well, the temperature deviation here, which this 13 degrees Celsius, shows the strength of the storm again. The warmer it gets, the drier it gets, shows how clear the eye is. So I could definitely say, just from this data, that we have a very, very clear, cloud-free eye. Alright, next column here is our wind speed. Again, this is the meat and potatoes. Alright, this is a southwest pass, southwest to northeast. So in the southwest pass I see winds out of the northwest, 300 degrees or just about 300 degrees. Light winds are, a little breezy, but start slowly increasing. In the southwestern eye wall, we get peak winds of about 97, gusting to 111 knots. And then they rapidly fall off, and that's because we're in the eye. Once you get in the eye, of course, what we're looking for is the lowest winds possible. 10 knots of wind, gusts of 18. That shows that the flight didn't quite go through the center of circulation. And of course, what's going on at flight level is going to be a little bit different than what's going on at the surface. That's why we want to back this up with a dropson. So based on this, we may actually have a little bit lower pressure. Of course, maybe 935 hectopascal, but we would want to double check with a dropson first. Wind direction will be variable generally in the eye, especially when the winds are so light. Then we ramp back up, and this is in the northeastern quadrant. Southeasterly winds. We get 138 knots sustained, gusts to 145. Of course, this column is our 10-second gust. We compare that with this next line. This is our step frequency microwave radiometer. You could see where we get into the northeast eye wall. Bring this up again. 138 knots. This is at 700 hectopascal in the eye wall, so a 90% reduction. We're looking at about 125 knots. That being said, let's take a look at this 145. 145, again reduced, gets you about 130. Incidentally enough, we do have an unflagged report of 133 knots, so I could easily see the National Hurricane Center going with 130 knots. They may go conservative and stick with 125 knots for their initial intensity. You get that information again from these three columns. Second to last column is our rain rate. Just a little bit of light showers starting off, intensifies in the eye wall. Right now you're seeing there in the southwest eye wall 32 millimeters per hour estimated by the microwave radiometer. Give you an indication for those metrically challenged, looking at about 1.25 inches per hour rain rate. Of course, get into the center, you're not going to have any rainfall because it's clear skies, and then get back into those heavy showers in the other side eye wall. And then this last line is our flags. Of course, double zeros are good. I do see a 03 here, so this tells me that this 60 knots is suspect, which makes sense. You've got 34 gust to 48 with a 60. Okay, that seems a bit excessive. Got another flag here where it's 92 gust 95 with 73. That might be a bit excessive, so it's flagged. So you want to take these particular lines a little bit less than you would the rest of them. So, all right. Now, one thing I did want to do is pull up a couple of websites. First off, National Hurricane Center. If you go to their homepage, go over to the left side, you'll see Aircraft Recon. What you're looking for is high density observations. You'll see there's a section for Air Force as well as NOAA. I'll go ahead and click on the Air Force one. Now these high density observations are also leveraged for other mission, training missions, for the winter storm missions. And just quickly taking a look at this one, a couple things I do want to point out. Notice the pressure, about 400 hectopascal. So they're flying very high, so this column now has become D value. So on this particular line, we're looking at about 396 meters above standard atmosphere. So what that means is this particular value, 7621, is about 396 meters above what you would normally get for this particular pressure readout. Really nothing else to note here. Got a couple of them flagged for the stepped frequency microwave radiometer, but it really, these observations come out every 10 minutes. It's really great to continue to monitor them. Mash that F5 button so you get the latest information. You'll continue to get that as the mission goes through. Now, one thing I like to do now, over time I've been able to, quickly look at this data set and be able to determine what the wind speeds are, what the pressures are. But sometimes it's great to get a visual, and one of the great sites I like to use is tropicalatlantic.com. Go over to our products. There is a live reconnaissance system there. You can continue to follow recon missions live. One of the great things is they've got a Google Earth plugin. Go over there. You can get a visual representation of what's going on. You can click on individual wind barbs and get a complete translated, dummy-proof readout of what's going on. You could also get RECO observations, vortex data messages, as well as dropsondes. And then another thing I want to look at or show you, this is the National Weather Service's website. This is a depository of bulletin headers. Now you go through here. This is the UR section, so this is upper air. You can see, like for instance, right here, URPN15.KBIX. This tells me this is a Northeast Pacific high-density observation. KBIX, that's just the backup for the Air Force. You do get some other ones, like here's one, PA15. This is PGUA. This is flying out of Anderson. This was a Western Pacific mission into Super Typhoon Megi. One thing is really interesting. You go down here, URPA15 RCTP. RCTP is the identifier for the International Airport in Taipei, and believe it or not, the Taiwan does fly reconnaissance missions in the Western Pacific. They don't fly fixed missions, but they do fly synoptic missions out and ahead of the storm. You can use this information and kind of get an idea of what the crew is doing. Some that they're starting to do anyway. So anyway, definitely plenty of stuff to use out there. Again, high density observations really shaped how we look at hurricane reconnaissance. Anyway, hopefully you get something out of this one. Next video we'll take a look at the dropsondes. Anyway, have a great day everybody. Take care. See ya.